Right, go. Thank you.
Okay, thanks for the introduction, Live. And hi, everybody. I'm a PhD candidate, as Live mentioned, right now at MIT, being advised by Dava Newman, Chris Hill, and Kay Crawford. My presentation is about my PhD research about machine learning for making accessible climate projections. And here on the right, you can see a machine learning emulator that tells us if we dramatically reduce deforestation, what would the impact be on the most local climate risks, in this case, flood risks in Houston. Now, this is a demo, so this talk will be about 40 minutes telling you what are the technological innovations needed to create such an emulator. And feel free to ask clarifying questions during the talk, and other questions probably the best at the end. So I'm doing this work because climate change does require immediate solutions. You're probably all aware there's a difference between 2-degree and 1.5-degree warming. At 2-degree warming, what scares me personally the most is probably 99% of all coral reefs are expected to face long-term degradation. That's only modeling the sea surface temperature effect on corals, not even modeling other aspects. At 2-degree also, we're likely to have 420 million additional people that would suffer from extreme heat waves. That's rather depressing, so we try to limit our warming to 1.5 degrees Celsius. And about 95% of all nations' policymakers have also agreed to this goal. So these policymakers now, they use climate models to guide them find the best solutions to adapt or mitigate climate change. Here in the US, for example, climate models can tell us what are the climate risks per region. And I'm living here in Cambridge, Massachusetts, and we can see here a 1.5-degree warming would give us this flood zone, and a 3-degree warming would give us this even worse flood zone. And this can now be used in Cambridge to analyze and prepare us for increasing flood risks in the future. It does, however, require a lot of climate model runs in the background to explore these scenarios. And the problem has become that climate models have simply become too large. If we were to run a climate model at very high resolution, Fourier did that. He went out and ran at 1 kilometer, and it took about 3 weeks running on a 5,000 GPU node supercomputer, consuming the same electricity a coal power plant would generate in 1 hour. And that was just to simulate one future year. So clearly that is too expensive for this sort of decision exploration that we are envisioning, where we can see the impact of multiple climate policies, multiple IPCC scenarios. Also too expensive for uncertainty quantification. And if you've ever worked with the CMIP6 data, we are left with a whole repository, petabytes of climate data that now it's a full PhD student just to explore the output of some climate models. So with this deluge of data and the innovations that we've seen in machine learning over the last 5 years, we're wondering, can data and machine learning help this problem? And IBM, Microsoft, NVIDIA, Google, OpenAI, all of big tech sort of see this as a challenge and as a possibility. They're all working on their thing. In this talk, I would like to advocate that working in climate emulators can be a really good idea. So here we can see another climate emulator. This emulator is called the MIT On-Roads model. It's designed by colleagues. It exists right now, and it lets us explore if we highly reduce deforestation, we can see the impact on the global temperature increase, decrease in real time. And this model is so good, it's been used by about 200,000 people worldwide to find out, to educate themselves about learnings like putting a carbon price out will have a lot more dramatic effect on the temperature decrease than maybe planting 1 trillion trees, a lot more direct effect. And this model has been used by so many people because it's very accessible. Maybe also similar to ChatGPT, the technology of GPT was probably around for 1 to 3 years, but ChatGPT has made this technology so incredibly accessible that now it's being used and hyped over all of media. This model is so accessible because it only runs a global average model in the background. So it's literally like it's one grid point that's integrated into the future. The issue is that we are accumulating inaccuracies through just having a 1D model, and also we only have this global temperature increase, which locally might look very different. The Arctic is experiencing way stronger warming than maybe Cambridge. So the question now becomes, can we come up with a climate emulator where we use machine learning to approximate a climate model with the goal of dramatically reducing the inference time of the climate model while maintaining accuracy? And here I'm using the word climate model sort of representatively for all kind of Earth system models within this climate pipeline. The general pipeline then is the general pipeline of developing such an emulator is we first go out and generate a large data set where we sample from initial conditions, forcings, parameters, boundary conditions. In this case, we used a flood simulation model called NEMO to simulate sea surface heights around the UK, and then have a lot of solutions over time and space and parameters. We then train a machine learning model to recreate the simulated data. And then we have this machine learning model, and the beauty of it now is that sort of all this data, all these gigabytes to terabytes to petabytes of data are now compressed in the machine learning weights in this model that we can use for inference to query new parameters, initial conditions, or boundary conditions at an accuracy that maybe has some loss, maybe 98% accurate, but therefore dramatically faster. In this case, our flood model was 45 times faster without doing further optimization. And I like this research because this climate emulation problem poses a lot of novel CS challenges. First of all, climate data is very high dimensional. Most of the data we deal with is a 3D vector over time, and then it can have up to 40 channels, such as velocity, pressures, humidities, aerosols that are integrated over time. And all the predictions we do have to be trustworthy, because in the end they're going to be used for these billion-dollar questions of where do we build a flood wall, which policies do we support within our whole country. And we have long-term time series. Integrations of climate require us to integrate for like 100,000 of time steps, and we need to develop CS models, CS emulators that are stable over this long-term time series. All of this sounds probably infeasible if not there were physical constraints, knowledges that we have discovered over the last hundreds of years that can help us build our machine learning model to make it physically consistent. For context, the temporal scales in climate, there is nowcasting, which forecasts on the scale of hours, weather forecasting on the scales of days to days, subseasonal forecasting on the scale of weeks to month, and then ocean and climate predictions on the scale of months to years to decades. And my work mostly focuses on ocean and climate predictions, but techniques are more or less applicable throughout the timescales. So back to this emulator, we want to develop a technology where we can have climate policy sliders and then predict the most local relevant climate risk, but by using physics-informed machine learning in the background. And this is a work that I started at MIT about 2 to 3 years ago, and over the years we've been supported by all these institutes at the bottom. So the general system architecture of such an emulator would look like this. We have a low resolution climate state sometimes in the past that we initialized, and then we integrate dynamics into the future with known differential equations, such as Navier-Stokes. These equations, these differential equation solvers, have as input some forcings which were calculated by a climate policy / energy model that outputs us CO2 emissions over time. Once we have this low resolution climate state in the future, that's usually about 100 to 10 kilometers, we can use downscaling, in the easiest case, linear interpolation, to have a high resolution climate state, and then feed that into a chain of impact models, in this case, like a hurricane track model feeding into a flood model, into a storm surge model that can spit out like a storm surge map for Houston. And then once we have the storm surge map, we can visualize it to make it accessible to many people. In a broad brush way, the current state is that integrating the dynamics can still be slow. In the impact model case and in the climate case, the downscaling can be inaccurate if we just use linear interpolation, and the visualizations in some scenarios are simply non-existent. So over my PhD research, we have done various works to address these three challenges and make dynamical integrations faster, but also a bit more accurate if we do it at low resolution, downscaling more accurate by using machine learning, and then flood models faster and created visualizations. Throughout this talk, I would like to focus on making dynamics faster and more accurate, then touch on the downscaling aspect on some preliminary works here, and if we have time, touch on the visualizations. Okay, so we're now at making dynamics faster, and this contribution is called Multiscale Neural Operator: How to Create Fast PDE Surrogates or Emulators by Learning Resolution-Independent Subgrid Parametrizations. That's a lot of words. The main idea is we want to model large-scale dynamics and then learn the correction by using learn a corrective term that brings these large-scale dynamics closer to high-resolution dynamics with a neural operator. Why are we doing this? Machine learning models are very fast, but they are data hungry, and we don't really trust them for extrapolation. We mostly trust these machine learning models for interpolation. So here, for example, we can see the ground truth simulation of this flood model that I was talking about, and we fit the machine learning model to it, and we can see this. It's more or less accurate. It's also fast, but we only trained this on data of 2 years, so we definitely would not trust it to extrapolate outside of any of these 2 years. So to increase this trust, we want to combine physics and machine learning. There's many ways of doing this, and here we're doing this by leveraging the known physics by assuming a low resolution simulation is available, and then all machine learning is used to learn this hard to model term, this hard to model parametrization term, which usually requires us to run our model at very high resolution. And parametrizations are also one of the largest sources of uncertainty in climate models. So while we demonstrate this work on more simple equations, we hope to scale it up to climate models. How does the math of these parametrizations work out? Ideally, we would want to learn the dynamics of all scales. So if we have some solution U and we have some differential equations demonstrated by this nonlinear operator, applying the differential equations to the solution would spit us out the gradient over time, and we could integrate that. The problem is that this high resolution, that simulating these high resolution dynamics, that's the thing that required 3 weeks on that 5,000 GPU node supercomputer. So we said, okay, let's just be satisfied by simulating our dynamics at large scale. So we introduce a kernel, a coarse grading kernel that reduces our solution and differential operator. Calculating it this way, however, we would still require the high resolution solution. So we pull this term apart and we say we want we apply the equations we know on the large scale state, but that introduces this commutation error term. And that term has been approximated through various analytical approaches over the last, I think, 20 years, and better ways came up for this. And with the machine learning advances being out now, the question is, can we build a parametrization that is more flexible and works across various models without every time having to derive an analytical term for this closure, parametrization, or commutation error term. So what we are left with are these dynamics where we simulate a corrected large-scale dynamics by assuming we have known large-scale dynamics and then have an add-on learned parametrization. Within the field of learning-based parametrizations, we can kind of distinguish in between resolution independence, parametrizations that require an auto-differentiable solver, which would require us to rewrite most climate models that are implemented in Fortran, and parametrizations that are non-local. If we use fully connected neural networks, most of the time they are resolution independent because they only apply because they are shared across every grid cell. But that makes them non-local, and research has shown that non-local parametrizations can be better than local parametrizations. CNNs and GNNs, convolutional neural networks and graph neural networks, they are non-local, but because of their fixed filter size, they usually have to be retrained once we change the resolution in our models. There's one work that overcomes these two challenges, but they do require an auto-differentiable solver in space. So by using neural operators, we overcome these three challenges. The architecture during inference that we're proposing now is that, okay, we have this known large-scale model that, given a large-scale state, we can query it and it predicts us the next large-scale state. It has that bias in it, so the neural operator takes as input the previous large-scale state and predicts the parametrizations, which is then added on, and then it can be explicitly integrated into the future. And the beauty of this neural operator is that it doesn't learn the dynamics in the spatial space, but it learns the dynamics in the spectral space, which makes it independent of the choice of resolution in the spatial space by learning the dynamics in this spectral space. It does require a fixed resolution in the spectral space. And we chose to use, there's various neural operators out there. We chose to use Fourier neural operators because they're good and very accessible and designed for this use case. And the architecture is that there's this input, this previous state, and then there's the output, the parametrization. At the edges of the architecture, we have linear transforms, which increase the feature dimension. So let's say, for example, we're just learning vorticity, a one-dimensional input, then this linear transform would make 64 channels out of this one feature input. Then we feed it into a chain of Fourier layers, and these Fourier layers is where the nice thing happens, where we have that lifted state, and then instead of applying a convolution onto this, a local convolution, a filter onto this state, we now apply a global convolution by transforming the state with a Fourier transform, then applying a learned matrix onto these Fourier vectors, and then projecting it back into the spatial domain, having a skip connection here, and then applying our nonlinear activation.
Björn, can I ask a clarifying question here?
Yeah.
So when you're saying this input state X, is that just this like scalar value at one latitude, longitude grid point, or is this Fourier decomposition done sort of over space? Or is it just, you know, the scalar value at one point is what is then multiplied by 64 different weights to make this P value?
The X is the global input.
Right, so it's a whole field, yeah.
So it's the whole field. And then this architecture has been designed so that this linear transform does not, it's independent of the resolution of the whole field. And then this Fourier transform is also applied across the whole field. And then you have your spectral states.
Yeah.
And then we're assuming a fixed resolution in the spectral domain.
So if you sort of changed your global climate simulation that you fed in, then this P operator would ensure that the same sort of spectral modes are activated in the feature space. That's why that's sort of the clever bit. That's almost the grid independent part then, right? And then the network is always working on the same Fourier modes, independent of what your source model is. Does that make sense? Yeah.
Yes, that does make sense.
Very cool. Thanks.
Okay. So we would like to demonstrate this, ideally on a climate model, but we started a little smaller. And we want to benchmark it on chaotic multiscale models. So we chose two models. One is the multiscale Lorentz 96, which simulates a global 1D atmosphere. And the other one is a quasi-geostrophic turbulence, which simulates equatorial atmospheric dynamics. The gist of the multiscale Lorentz 96 model is that we have two scales, the blue one and the orange one. The blue one is a large scale simulation, and then the orange one is the fine scale simulation that is coupled with a large scale simulation on every time step. The equations of this for this look like this. We have the large scale dynamics at the top and the fine scale dynamics at the bottom. The large scale dynamics simulate things like advection, diffusion, some forcing. The important thing is this term here in the back, which in this multiscale Lorentz 96 model simulates the subgrid parametrization. And calculating this term has quadratic runtime complexity because it requires access to every single high resolution state. And we say with our neural operator, okay, let's not simulate the fine scale state. Let's just approximate this subgrid parametrization based on all the previous large scale states. And that's where the runtime decrease comes in. We create a data set by running a warm up of the Lorentz 96 equation until a statistical equilibrium is reached. I think in this case, I ran it a bit too little, but we then collect snapshots of the high resolution simulation. We can collect these snapshots every step or every 100 steps or what's or not. And then we generate ground truth parametrizations by subtracting the low resolution simulation from the high resolution simulation. So on every time step, we either run high resolution and low resolution time simulation, or we have some way of knowing what the low resolution simulation would have been like to generate this parametrization. That leaves us with a data set of low resolution inputs, low resolution simulation inputs, and ground truth parametrizations that we want to learn. So now we can discard the high resolution simulation. And we fit our model to do this mapping from low resolution input to parametrization and then roll it out after training. And we can see here in this plot over time where I picked one state with that our model is more accurate than current baselines. One of the ground truth in this plot is this black curve, and our model is this yellow curves that can follow this curve for approximately 550 time steps. The other models diverge relatively quickly, and the other models here we chose are machine learning based parametrizations, which is local using the losing a fully connected neural network, and a linear regression fit, and a climatology, which is just predicting the mean. If we measure quantitatively the accuracy of our model over, I think, 1,000 samples, we can see that our model is about 4 times more accurate than the other existing parametrizations. Our model is also faster than the ground truth solver, which we said would have quadratic runtime complexity. Our model says if we increase the grid size and we plot it over the runtime in seconds, we can see that there's a quasi-linear runtime complexity that is dominated by the Fourier transform here, taking quasi-linear time. Stable in the sense that our model does not diverge to infinity over when rolling it out over long terms is also the case. If we plot the error over time, we can see that the forecast that our forecast is better than an average prediction for about 600 time steps, and then we can see that our model does not diverge to infinity. I do want to point out that the model we right now developed is myopic. It only takes the previous time step as input and predicts the parametrization. There's a lot of improvements that one can do here by incorporating various ways to learn the temporal scales better. What we wanted to show is, okay, neural operators can be better for learning parametrizations than fully connected neural networks and other parametrizations. But this stability can be drastically improved by doing things like the push forward trick to incorporate time in the loss function, or also by incorporating various input steps in the various time steps in the input. We started developing this model on the quasi-geostrophic turbulence. And here we have the input, the low resolution input. This is the ground truth parametrizations that we are trying to predict. Climatology, a mean prediction would just predict nothing because the mean is 0. And then our prediction here, we can see that it kind of gets the large scale patterns right. It's very interesting that we can see this parametrization here has a lot of little bumps, like a lot of high frequency modes, and they are nicely approximated by our model. The more thorough evaluation I still have to do. So I mentioned the limitations. It's currently a myopic model. We can definitely improve this by incorporating some time. The current code does assume an accuracy-based grid just because of the Fourier transform that's currently implemented in PyTorch, but there does exist non-uniformly spaced grid Fourier transforms. I think what would be very exciting to extend this work to is to enforce hard physical constraints in the parametrization term we learn, because this parametrization term in some equations is very well studied and we know things about it. In some cases, it can't be smaller than 0. In some cases, it has to have a 0 mean, things like that. We can try to enforce maybe with in or equivariant networks. We can also leverage the runtime increase for some uncertainty quantification. So that is the summary. We learned a multiscale neural operator with the goal of making it faster, resolution independent, and a non-local parametrization. We have about 10 minutes left. So in these 10 minutes, I would like to talk about the downscaling part. Here we're switching gears a bit. Now we find ourselves in the Antarctic, and this is a collaborative project with Columbia University. And the problem in the Antarctic is that ice shelves prevent ice sheets from slipping into the ocean. Ice shelves, however, can collapse. So when an ice shelf collapses, there's more ice sheets slipping into the ocean, possibly increasing our sea level. And surface meltwater can indicate when an ice shelf collapse will happen, and people are studying this. It makes it difficult though to study because we only have surface meltwater maps every 16 days or so. There does not exist daily high resolution maps of surface meltwater. And here on the right side, we can see Antarctica the Larsen Sea ice shelf. And here, this is what such a surface melting would look like in visual imagery. And we say, let's formulate this problem as a super resolution, as a downscaling problem to see if we can generate these ground truth parametrizations. So as input, we collect a simulation, the MAR model, which runs at 6 kilometers, passive microwave satellite observations, which are available at 3 kilometers, and then visual imagery from MODIS, which is available at 500 meters, but has some cloud, some areas that are masked because of clouds. So this ground truth, these inputs are available daily, but they're low resolution. At the same time, what we have available is Meltwater derived from Sentinel-1 radar SAR observations, which are at 10-meter resolutions, but we only have these every 16 days. So now we designed the super resolution task, which says, can we use these data streams as input, feed them into a deep generative vision model, and then output this Meltwater, let's say at 100 meters first, for all the time steps in between the observations that we have available. And there's previous works that do this locally. They just take one point as input, and then they predict what the surface Meltwater at this single point would be given these inputs. And the question here is whether using a deep generative vision model, which has a more global receptive field, a more non-local receptive field, can improve the accuracy, can improve by correcting some large-scale biases that we have in the data. So within deep generative vision models, we have a lot of choices. And here, for example, we have a low-resolution image, but a low-resolution image has multiple possible high-resolution ground truths, because a high-resolution image, coarse-grained, like multiple high-resolution images, if we apply a coarse-grained filter, would look the same if we in the low-resolution world. So there is some form of stochastic prediction task here. So this presents the image manifold of possible high-resolution scenarios. And in the first works that came out, like 2018, used convolutional neural networks with a mean squared error loss to predict what a high-resolution scenario would look like. But mean squared error is known to sort of find the average in between all these high-resolution scenarios. So then there came out GANs, generative adversarial networks, and they then were better at this super resolution scenario, because what they would more or less do is kind of just pick one of these high resolution scenarios that could be true and then predict that. But that also makes us lose out on all the other possibilities that we could have had. And in surface meltwater, we might be very interested in having a distribution over what are the possible values within our grid cells. So there comes these stochastic methods of predicting high resolution scenarios. So first there was stochastic generative adversarial networks, but they often suffered from mode collapse, hallucination. It was very difficult to train them because of like convergence failures. And sometimes we had to go into the loss function to avoid these convergence failures. So normalizing flows were better in that. They were easier to train, but they did take very long to train, like usually around a week to fit on a normal size data set. They also have a lot of model architecture constraints, which makes it hard to fine-tune them for specific tasks. So recently we saw the hype in diffusion-based models. Diffusion-based models, you might have heard it through Stable Diffusion, which was like an app you could use, and you could type in a query and it would give you out some form of nice image. So here, these diffusion models, we think about, can we use them for super resolution? And Zaharia et al. Did that on images, and we can see the output does look very real. If this is an input of a kid, then this is the output, whereas this was the original. And we are now training, so we have now took this diffusion-based model, we started a year ago. There was no implementation available, so we coded up a diffusion-based model and tested it on our WISO super data set, which is wind and solar data set, because we are still processing the surface meltwater data set. And we can see in some preliminary results that, like on the bottom, this diffusion-based model does generate us various samples of one low resolution images that are distinct. Like, for example, here we can see no high frequencies. Here we can see some high frequencies. And we can see that there is a lot of high frequencies introduced, some high frequency detail here, here, here. So this is work in progress. I wish I would have more results to show you, but I think I did decide to show it to you because I think diffusion-based models have a lot of potential, and it will be, I think they can make a great impact onto weather and climate space. Okay, thank you so much. I don't think we have time to dive into the visualizations. So how about we stop it here, and I can take any questions about this multiscale neural operator or DailyMelt, our super resolution models. Thank you.
Okay, we've already got a question online. Thank you very much, Björn. That was really great. Miranda, do you want to just go ahead?
Can you hear me?
Yeah, we can now. Yeah. Go ahead.
I put it in the chat. I was just wondering whether there's any available code for the MNO model somewhere online.
The code I'm planning to release in like summer.
Okay.
For this MNO, but what you can use in the meantime is there's a nice implementation of the Fourier neural operator available if you Google Fourier neural operator GitHub.
Yeah, I've got access to that one.
And there is a nice implementation available of this quasi-geostrophic turbulence by Hugo Frézat. If you Google QG torch.
Sorry, how's it spelled?
QG torch.
Okay, thank you.
You're welcome. Also, you can email me and we can work together on making things happen. I think that might be the easiest way.
That's great. Do we have another one online? Should we go to the? You were very quick. I think I saw another hand. No? No. Hallucinating hands. Yeah. Generative.
I think that was my hand.
Your hand went down. Okay. So, I mean, I have a question then. So, these are great examples, Björn. I think also thank you for being so clear about how they each work, these different techniques you use, because it really helps. You know, that's what we want to do in this community, is learn how to do it ourselves. So I had a question about the diffusion stuff you done here at the end, where it's sort of similar to the GANs. Like, how do you know that your sort of the space that you mapped to that is real? You know, that it's generating what's actually physically real, right? Because as you say, you can coarse grain and get the same coarse grain from many different satellite images. Is there a way of measuring somehow, like how good is it at hallucinating? What would you do in a geophysical field? I don't know if you could go into that, because I know people have done it in the image application, but like what are your thoughts on that? Basically making people more confident at using them, right? Because that's presumably something to look out for here once you start training them.
Yeah. So maybe if I can rephrase.
Yeah.
Can you still see my screen?
No, we can see your face at the moment and around that.
Okay. So I think basically what you're asking is, within this image manifold, only some of these high resolution pictures will be physically consistent. How can we constrain our model to only pick the physically consistent ones?
Yeah, does that happen just magically, or do you put that in somehow? Sorry.
Yeah, so right now it happens through like a mean squared error-based loss function within a generative process of the diffusion-based model that's fit to noise. But it's only happening approximately right now with soft constraints.
Right.
There is other ways of bringing the physical consistency in explicitly. And I think we can choose in between hard constraints and soft constraints. For example, David Rolnick and Paula Harder brought out a work that embeds hard constraints on the output, sort of in like a post-processing way, where you might have the last layer of your neural network to make all negative outputs be positive if your output can only be positive. So that's one way to bring in hard constraints. Other ways of the soft constraints would be we have some form of equation available that we can feed in our high resolution output, and we feed it into an equation. This equation might be conservation, might be divergence of velocity. And if this equation is non-zero, we know that our output field is not incompressible, and we can penalize our model on that. So that would be an example of a soft constraint.
Yes, you could put that directly in the loss function, and then as well as learning to satisfy that, you also can sort of measure it. Like, you know that all the things you've generated in training, they were non-divergent, say, and so you can feel confident that that's how it will behave when it's set loose on data it hasn't seen. I see. Okay, that's cool.
Right. The challenge though with it is to find and this is where, you know, collaboration becomes important. I'm more the expert in machine learning. The challenge, I think, is to find some set of equations that are applicable in the domain of super resolution that we want to work on. So in the surface meltwater, we are thinking about what makes a physically consistent surface meltwater map. Like, yeah.
Variant networks, so enforcing physical constraint with equivariant networks, I think that future work you mentioned. So could you elaborate on that idea?
Yes. So do I understand correctly that you're asking, could we use equivariant networks to have a physically consistent downscaling method?
Yeah, what I thought I saw on your slide that you said that future work would be to enforce physics via equivariant network.
Yeah. Yeah. So the idea of equivariance is if we take our input and we apply some transformation to the input, then the output will have the same transformation. So if we apply, for example, translation on the input or rotation, then the output should be similarly translated or rotated. And that can be used to enforce, like in this quasi-geostrophic example, I think that's a good one. If we would rotate our input, we would also expect our parametrizations to be similarly rotated. And using an equivariant network, we could enforce that in the architectural constraints as a hard constraint, I believe. The other way would be to do it via data augmentation, where whenever we load in our image into memory to feed it into the data loader, into the model, we can apply a rotation to the input and the output and hope that the model sort of learns that if we rotate our image, the output will also be rotated. And that's a soft constraint.
Did you try to apply a soft constraints like pins to your model? Have you had a try?
Yeah, in this case, I think it's it became relatively standard to use data augmentations. whenever we do some vision work, there is in the other work that I didn't talk about, we generated these flood maps where as input we have a pre-flood image, and as output we have this is how the image would look like if this area would be flooded. And the input also has the output of a flood model so that we can have physically consistent and trustworthy predictions. And here we applied a lot of data augmentations such as a color jitter, rotation, translation, blurring to the in and output. In the case of quasi-geostrophic turbulence, I also tried it with the rotation because theoretically it should be the same, but it actually decreased my performance in this case, which I think is because the data set wasn't large enough. So I think I can make the data set larger and then have apply the rotation, and it would increase the accuracy.
Yes, go ahead.
So, according to your experience, how do you to improve this machine learning exploration ability? I mean, you predict more time scale outside your training space. Thank you.
Did you catch that, Björn? Yeah.
Are you asking if we had a test set or validation set that would test generalization performance?
Yeah, exactly.
Yeah. Partially. So during dataset generation, we have chaotic equations, and we run these. We initialize the chaotic equation somewhere, and then run a warm-up, so data that we don't incorporate in the training data set until there's some statistical equilibrium reached. And then in an ideal world, we collect snapshots of this simulation by just running it very, very long into the future, and then adding a snapshot of the solution every n time steps, where we can measure, where we design the time that we leave in between every sample to be as decorrelated as possible from the previous sample. So this is how we generate a training data set, where then at inference, we can use any initial condition of this Lorentz 96 equation, and the output will have a good accuracy, because the initial condition was within this set of long-term time integration, which should have covered sort of like the whole space. And I think the learning here is that whenever I use machine learning, I have to go like an extra step, so that I design my training, validation, and test data set so that my test and validation is within the training distribution. So here, now this allows us to generalize in time. Like I could predict future time steps that I've never seen before, but it's not actually an extrapolation. It only sounds like an extrapolation, but the way I designed the data set, it is an interpolation task. I hope that makes sense.
Yeah, you got a thumbs up. I have a very quick question here at the end, Björn. When I first really talk about the Fourier sort of neural operators and how you use them, I was really excited because Fourier modes sort of seem physically like very understandable and interpretable things physically, because you can look at what Fourier modes are sort of, a lot of times we look at Fourier decompositions of our physical fields to study them. And so I was just wondering if you've ever done that with this work in a way. I guess it's a bit hard with that stochastic system, but when you're looking at the flow, whether you actually naturally end up seeing certain modes excited within the network, and whether this is something you can use. Because you can imagine training this and then actually using it to learn how to write down the sort of equations for the subgrid flow, right? I think I mentioned that when we talked at EJU actually as well, like looking back a bit. But I was wondering what you think of that idea now. You spent a bit more time with it. Does it make sense?
I think that's a cool area. Like, I'm talking about climate emulators and saying they're useful for decision exploration or uncertainty quantification, because once we fit them to the climate model, they're now faster. But they do have another advantage, which is once we have trained this climate emulator, it has learned some form of compressed form of the equation set that we had, of the data set that we trained on. And this compressed form has some very nice nonlinearities that were learned that can, for example, tell us about some spatial correlations or temporal correlations. And there is a research field that then looks into these features that we learned and thinks about, are these features interpretable? And we did a work where we had graph neural networks and we fit them to train to do subseasonal forecasting, in this case El Niño La Niña. And we found that the eigenvectors of the learned adjacency matrix of this graph neural networks can show us nice correlations that we would have expected for El Niño La Niña. I haven't done that for this Fourier work, but I think it's still a cool direction.
Yeah.
I think it requires a lot of domain expertise. So I think that is something where, in the graph neural network, I work then with an ocean scientist who knows El Niño La Niña very well to think about what are these features. And I think in this case, we would have to find like a turbulence scientist who knows a lot more about quasi-geostrophic turbulence.
Yeah. I would dig more into this. Sorry, but I can see Sam's got a question. I feel like, Sam, you should get in just the last minute. If you're still okay with it.
Yeah, sure. I've just got a quick question. Thank you for a very clear talk. You've obviously worked on some really interesting things. You don't mind, I've not got a question about your work, but more of a general one about the ways of working in your research environment. It's like, particularly when you talked about like training generative models and coming up against mode collapse, it reminded me of debugging issues of my own and being constrained by like computers that we're using and people to speak to and stuff. So yeah, my experience in machine learning research is that we tend to be quite siloed and suffer in silence when it comes to doing machine learning in our own work. The SciML group is one way that we're trying to escape this. So my question is, could you perhaps walk us through how and where you run your models, how your research team operates, and whether you have any good tips on making good progress in machine learning and working more efficiently?
Great question, Sam.
Yeah, good question. Let's think. So I feel you, because machine learning has some form of black magic to it. Like we take this model from the internet and then we want to make it work on our own data, but we realize very quickly that some of the hyperparameters, we might need to tune them. And now what are the hyperparameters that we do need to tune? Is it the learning rate? Is it the number of layers? There's all these choices that we have. And I think one way to go about this is, like, one way I like to do is, like, text the authors, how can I tune this model? Or find somebody. MIT has a lot of people that work in AI. There's like, it feels like half of the university is just doing AI these days. so I can find like a friend who's doing that. My personal advisor hasn't too much experience in the hyperparameter tuning of these novel models, so it's more like similarly aged peoples that I'm looking for. And then we do have quite large supercomputers that we run everything on. So usually I try to fit the model once. On my local CPU, I develop everything, and then I train it on a larger data set within the supercomputer, and then I code up like a hyperparameter search that sort of has all these choices, learning rate, decay, number of layers, and then do like a random sampling within those hyperparameters to find the best choice. But it is a lot of work from like, oh, we trained our model once to we have this perfect model that is fine-tuned for this data set. It does take a lot of time.
Cool. That's very helpful. Thank you.
Right, I think we should wrap up there. That was really excellent, Björn. Thank you again for taking some time in your morning to give us this great talk. So should we give you a last clap?
Yeah, thank you.
So, I would just say here at the end, so obviously, you know, we're all sort of virtually, a lot of people, especially Björn, you know, is online over the other side of the ocean. I know Björn is very keen to collaborate with people if people are interested in using the techniques he's talked about. I think the best way is simply to get in touch with Björn and just email and then, you know, organize a one-on-one talk. I know you're keen to do that, and also share any code or, you know, work together. And I'd say, Björn, if you want to see a bit about what we do, we have a website, we can see our faces. I know you haven't heard what we do, but we work in very different areas. So you might also find that you want to know something a bit more about a technique and application, you're welcome to contact us. But thanks again, everyone. Thanks for coming. I hope you have a great weekend. And enjoy the rest of your day, Björn. Bye.
Yeah,
Bye.
Thank you so much for all the helpful questions. That was very fun.
Right. Yeah, it's been really fun.
Bye.
Thank you. Bye-bye.